Dear students, I hope you are doing well along with your family. Today I will discuss with you a new topic, and that is term diagrams. It is not really that new because we learned about configuration and then we also learned about terms and how to derive terms, ground state term and excited state term. Okay, but today I'm going to talk about another thing, how these terms are splitted when they are placed in a crystal field or in fields of different geometries. I'm dividing this lecture into two parts. In part 1, you will learn how S, P, D and F orbitals split up in crystal field or ligand fields of different geometries. You have already learned about it when I gave you lecture material on crystal field theory, where you learned how d orbitals split up. We never said anything about p orbitals and s orbital and f orbitals. Today, in part 1, I will explain that as well. In the second part, you will learn how S, P, D and F terms, they split up in the crystal field in different symmetry. Regarding splitting of orbitals, you have already learned in your BSc and MSc classes. And even I have sent you material on crystal field theory. The big question is how s orbital and p orbital split up. We know very well how d orbital split up in different geometries, that is in octahedral, tetrahedral or square planar, but we have never learned how s orbital and p orbitals split up. We have not even learned how f orbitals split. So in this lecture, you will learn in brief splitting of orbitals, SPDF, and splitting of terms, S, P, D and F terms. Splitting of s orbital, well, I think you already know about it. S orbital is of spherical symmetric shape. The second thing is it is non-degenerate. By that I mean, okay, it is only one. It's not 3 like p orbital, 5 like d orbital, it's 1. That's why we say it is non-degenerate. Okay, and it is not affected in any crystal field. Reason being, supposing in this diagram you can see this is x-axis, this is y-axis and this is z-axis. Okay, when the ligand is coming from here, okay, if it is affecting 10 units, this ligand which is coming, it is also affecting 10 units. And one which is coming on y-axis is also affecting 10 units. So this orbital is equally affected. So no splitting will take place. Splitting of p orbitals, the shapes of the p orbitals is shown here. There are 3 absolutely equivalent p orbital, px, py and pz. They are all pointing mutually at right angle to each other. We are already familiar with this, and in figure below you can see very well. See this one. I have put a metal here and which contains p orbital, and here the ligand is coming in the z direction. Okay, this ligand is coming on x-axis and similarly y-axis. When it comes from z-axis, the pz orbital will go high in energy. When it comes from this, so px will go up in energy, same units, and similarly is y. So all three p orbitals, they are equally affected. So you can see here in another example, cobalt complex. Okay, this ligand coming on x-axis, this is y, and this is same ligand, same effect. So same effect should go on all the three. That is, okay, they are equally affected. That would mean that there will be no splitting. Okay, the same is applicable when we talk about the tetrahedral complexes, where there are four ligands all approaching between x, y, and z axis. Now you can see here this ligand, okay, this is x axis and this is z axis, and okay, so all these four are affecting what? The p orbital which are in x, y, and z direction. So they are being affected equally. So the p orbitals are not split in octahedral and tetrahedral symmetry, but p orbitals do split in square planar. I will explain in a minute. See, I have shown here p orbitals. A square planar, I mean, okay? The ligand is coming on x-axis, ligand is coming on y-axis, no ligand is coming on z-axis. So there is no effect on pz. Pz orbital doesn't go high in energy. That means it is stabilized, and you can see I have shown it here. Okay, here is a pz orbital. No ligand is coming, whereas there is a ligand coming here, here. No ligand coming here. So effect is on this axis, this p orbital, and this p orbital, but not on this. So this is what exactly is. So no ligand is approaching the z direction. Therefore, pz orbital is stabilized, goes down. About splitting of d orbitals, I don't have to say anything. You have learned it many times. Okay, they do split. Reason being, okay, there are two sets of orbital. Okay, there is one set which is along x-axis, y-axis, and z-axis. You can see here. Okay, this lobe is on x-axis and y-axis. This is on z-axis. But if you see this one is between the axes. Okay, so similarly xy, see this one, these lobes are between the xy. Okay, so anything which is coming on the axis will be affected, but anything which is coming on xy, that will affect only the orbital which are between the x and y direction, xz direction, and so on and so forth. Okay, the lobes See, the lobes of the dxy, dxz, and dyz, these are three. 1, 2, 3. What about them? All line up in a quadrant between the axes. Okay, they are not on axis. Okay, and there is no electron there. So these three orbitals form a T2G set, whereas this is different from that. That is on axis. This form EG set. In most cases, the d orbitals are degenerate, but sometimes they can split into EG and TG. Okay, having different energy. I don't need to explain. I have explained it before as well. Okay, so any orbital which is on the x-axis and y-axis and z-axis, since ligands are coming, it should go up in energy. And what are those orbitals? Those are this, dx square and dy square. The remaining should remain down, and this is exactly what you see in the diagram here. I've shown here. Okay, d orbital, 5d orbital. Okay, when the ligands approach, all they go up and then they are separated. T2G lower, EG up. Same thing here, but okay, octahedral and tetrahedral. D orbital, okay, splitting. Next, splitting of f orbital in octahedral. It is comparatively more complex, but it can be handled and explained by using group theory. Note, I have not taught you yet group theory, and it may be somewhat difficult to explain it here, but you see, there is a simple way that whatever SPD and F orbitals they split, SPD orbital, same way they should also, because F orbitals they also have directional character. D have directional, P has they split, they should have. So all I want you to know is F orbital split up in T1G, T2G and A1G sets. Okay. Some of the example which I am showing you here of the SPD and F orbitals splitting in octahedral symmetry. It is shown here in the table. Okay, this is the type of orbital, S orbital. Orbital degeneracy is given by 2l plus 1, you know very well. Okay, for S, L is equal to 0, so it is 1. It is non-degenerate, no splitting, okay, in octahedral field. P, okay, 2l plus 1 it degeneracy is 3. That means there are 3 ways in which you can put an electron, and this orbital degeneracy is 3. Or we say threefold degenerate. No splitting in octahedral explained before. D orbital they do split further, okay, into T2G set and EG. No, I explained before T stand for triply degenerate. 3, I have put 3. E stand for doubly degenerate. 2 orbitals, same energy. So I have put 2 here. So 3 plus 2 equal to 5. 3 plus 2 equal to 5. Okay, d orbital 5. F orbital, you just have to remember they split up into T1G, T2G and A1G. This is the triply degenerate 3, triply degenerate 3 and non-degenerate 1. 3 plus 3 plus 7, 7. Part 2 is splitting of terms. Okay, well, don't get scared. You have learned about the terms S, P, D and F terms in okay, before in my lectures before, how do they split in different geometries? We learned how orbitals split up, but how do these split? It is very easy to remember. Terms split per exactly the same way as orbitals split up in a given field. If d orbital split up in T2g, so d term will also split up into T2g and Eg. If f orbital split up in T1g, T2g, and if f term will also split up the same way. I have shown it here, please. All we do is instead of using the small letters A, E, and T, we use capital letters. This is S term. So, no splitting in octahedral field, fair enough. It should be represented by capital A1. P is 3-4 degenerate, no splitting in octahedral, okay? And this, it splits up into T2G and EG. We have used capital letters here, okay? And then finally this one, T1G, T2G, capital letter, not small, A1G. So this is all. So term diagram, this is the topic actually. That was the heading of the topic, and that was the term diagram. So now I'm coming after explaining so much D1 in octahedral. Okay, what the D1, what terms it has. This is the configuration of a D1 system, titanium 333. So it can be shown here. You can, okay, just find out its ground state term. Okay, L is equal to 2, and therefore it will be D term. There is one unpaired electron, so spin degeneracy will be 2. Okay, so it will be the free ion term of D1 will be D2. In octahedral symmetry, okay, doublet D term splits into, again, as I have said before, T2G and EG. Now please note, we have put 2 here and 2 here. There is a 2 here. Whatever the degeneracy here, the same comes on this one as well. These are called group theoretical notations or terms. This is spectroscopic, S, P, D, and F. Okay? So spectroscopic terms further split up into group theoretical terms like this. So here I'm all showing is the spin to the same goes here and so on goes here. So possible transition will be from TTG to EG2. Okay? And only one absorption band predicted. See here, ground state, excited state. I have shown it here, ground state, excited state, and one band. And that is the whole thing. Term diagram, so, and I'm saying what will be the term diagram? The ground state is D2, and term diagram will be D1 ion gives D2 term. It splits into 2 energy levels, T2G2 and EG2, and there will be only one. And one band. And thank you so much.